Mohammad Arman, presenting our paper titled A Deep Learning Approach for Reconstruction of Color Images in Different Lighting Conditions based on Autoencoder technique. Object detection has achieved considerable progress in terms of achieving higher success rates in detecting various objects. Automated object detections includes detecting real-world objects such as people, animals, roads, signs, colors, etc. So there are some issues regarding object detections which include color intensity, restorations, light intensity, and so on. In this paper, we shows that the shades of objects and colors of the sunlight for the sunlight is changing by the time of the changing the position of sun. For example, an object represents its exact color at noon when the sun is at its optimum position. However, the same object looks very dull in color in the evening when the sunlight is very low. So approaching this problem, we input the method of autoencoder to retrieve the color detection problem. Object detection has achieved progress in terms of achieving higher success rates in detecting various objects, such as detecting objects like people, animals, colors, etc. So there are some issues regarding object detection like color restorations, light intensity, and so on. It is seen that the color of an object changes with the changing lighting conditions of daylight. For example, an object represents its exact color at noon when the sun at its optimum position. However, the same object looks very dull in color in the evening when the sunlight is very low. There are some other issues like self-driving cars. While a car drive on the road, the car might drive on the rainy days or foggy days. So it faces some difficulties when detecting an object automatically. To overcome this issue, we construct a methodology which we developed by the autoencoder technique. In order to develop a proper efficient reconstruction technique in different color variation for images, pictures of objects from different directions has been taken, which we called reconstruction of color images. That means we take an image as input and reconstruct the images from various perspectives of the autoencoder. Then the output shows the probable results of various lighting condition to our desired lighting condition. To continue this methodology, we develop our own dataset. There are some work which is already done for detecting an object, such as light intensity and foreground object detections, vehicle color recognition, and road sign recognition. When a vehicle is running towards the road, it detects the vehicle and along with the road sign. As a result, it imagines an object in front of the vehicle. Also, there are some works done by the low light enhancement, such as night vision technology. So now we are talking about our dataset. The dataset in this model, we used our own dataset, which we took the photos of our own. The original image of the dataset is 1920 by 1080 pixel, and the images was captured from 5 different angles. So we took the 5 different angles to object the color of an image from various perspectives, from various sunlight positions, so that the image variation can be visible more accurately. Then the image quality and quantity, which was almost 10,000 images we captured for our dataset. So for running the dataset into our model, we use 2 kinds of pixel size. One is 148 by 196 and another one is 380 by 420 pixels. The reason to take 2 different pixel sizes was our hardware limitation. Our hardware didn't allow us to process such big pixel sizes. That's why we choose these 2 different pixel sizes. Also, there was a reason to choose these color pixels, which was to show that the larger pixel shows better results than the smaller pixels.
Hello everyone, I am Hasibul Hassan Shoboj. Now I am going to talk about our proposed methodology to get the proper efficient reconstruction technique in different color variations for images. We took pictures of objects from different directions, and the color of the objects varies at different times of the day. To produce more color variation, five different directions are used where the color where the object was placed centrally and the camera was moved in different directions to get an accurate color profile. By training those images in autoencoder, the autoencoder reconstructs its output from its input, and this autoencoder has three parts. And in the first part, which is called encoding part, the image gets resized in a smaller version, and then their bottleneck part. Bottleneck part is the input of the third part, which is called decoding part, and the decoding part just outputs the desired output. And in this proposed methodology, this proposed methodology used ReLU and sigmoid function as an activation function, and Adam optimizer is used and as the optimization algorithm. And then I am talking about the structure of the proposed model. In this figure, the proposed model consists of two main techniques which we are seeing: the image processing and autoencoder. Okay, now I'm talking about the image acquisition part. Image acquisition defines the first part of the model where the image dataset is collected in raw image format with a pixel value of 1920 by 1080 pixel. In our research, fruits of different colors are used as the objects, and they were placed under sunlight without any overshadowing hindrance. The camera was placed from different directions to capture different directions color profile of the object. Throughout our whole paper, we have termed direction as angle, and the five angles represented in our research represent the five directions where the camera was placed to capture different side of the object. Okay. Once we are done with our image acquisition part, all the images are now sent to the next part, which is image preprocessing. And the first part of preprocessing is the image resizing. Due to our hardware limitations, our images are resized into two different pixel dimensions, which is 180 by 196 and 380 by 490 pixel size, where we have mainly shown the result for 380 by 420 to validate our theoretical approach. After the initial researching of the image, later part contains the image color space transformation from BGR to RGB. This approach is taken in our model due to the image importing mechanism of OpenCV. As you are seeing in this figure, there are autoencoder part, and autoencoder has three part. As you are seeing, there are encoding layer, bottleneck layer, and decoding layer. And we will talk about autoencoder part, autoencoder descriptively in now. An autoencoder is a technique which attempts to rebuild its output as much as close to its input. It has mainly two parts, such as encoding and decoding. And in our autoencoder, encoding layer consists of three encoding convolutional layers. Our model works by running max pooling layer after each encoding layer, and third encoding layer sends the output of the third layer to the bottleneck layer. This part of the model compresses the image by taking the significant features of our image. And as you will be as you are seeing in the figure, in our first, second, and third encoding convolutional layer, we have used 60, 64, 32, and 16 filters respectively with a weight matrix of 3 by 3 dimension. In a whole, encoding layer is using the downsampling technique to resize its image in a lower dimensional image, and then it passes to its images to the bottleneck layer. Bottleneck layer is also known as latent view layer, represents the final reduced dimension of the input image, which was provided in the input part of the image. Bottleneck layer is considered the most significant part of the autoencoder. And bottleneck layer passes its resized image to the decoding part. And now I am talking about the decoding part of the autoencoder. Decoding layer works by performing the final stages of convolution operation, and decoding layer outputs decoding layer passes its input trained input to the output layer, and the images dimensionally increases, and the image is resized to the original input image, and upsampling is used in this decoding layer. And in the decoding layer consists of the the decoding layer we used it consists of three decoding layers. In the first, second, and third convolution layer, we have used 16, 32, and 64 filters respectively, as you are seeing in the figure, with a weight matrix of 3 by 3. Stride 2 is used to maintain the ratio of max pooling. It helps to reconstruct images. Now here comes the output part. The output of our model depicts the output image in size of 380 by 420 pixel. The output is in RGB format, and from the BGR format we have reconstructed it. And for instance, if we give an image of an afternoon lighting conditions, our model provides output for an image of a noon lighting condition, and that's how our model works, and that's how our you get our output. Our model can generate two kinds of output depending on its input. For instance, one output defines the afternoon lighting condition, another output defines the noon lighting condition depending on its input, and vice versa. Thank you.
Hello, my name is Paul Gomez, and I am going to talk about the result analysis section. In the result analysis slide, we can see that there are two different image sections for two different pixel ratios. The left image contains the pixel ratio size of 380 into 420 pixel, and the right side of the image contains the 148 into 196 pixel ratio. Both of the pixel ratio represents three separate sections: original image, resized input image, and output image. As mentioned by my peers, we can see that there are five different angles: east, southeast, south, southwest, and west. These angles represent the exact position of camera where the pictures were taken from. This represents the different sunlight directions, and we can also see the effects of these angles for different pictures. Furthermore, the pictures represent the input images of afternoon images and output images for the noon images. The afternoon images are first resized into their respective pixel ratios, and the output image shows the noon images which we have transferred through autoencoder and reconstructed to accurate color accuracy by training different angles to different processes. To further enhance the concept of using two different pixel ratios, and how we have used this to mediate the fact that with greater hardware or with better hardware we can achieve higher accuracy results, we can see the following slide where the RGB histogram is used to differentiate two different pixels and their color accuracies. In the left image, you can see that the images and RGB histogram shown for 148 into 196 pixel ratio, and in the right side we can see that the pixel ratio is shown for 318 to 420 pixel. In the left image, the bottom image is the output image, and the upper image is the original image. We can see the reconstructed image is not as close to the original image, and it is quite blurred in relation to the original image. And in the left we can see for the 380 into 420 pixel that the original image is closer to the reconstructed image, and the color histograms are also quite accurate and more closer than the 148 into 196 pixel ratio. This represents the fact that our model works for better images and provides better accuracy for higher pixel ratio, provided we have a upgraded hardware system. Now for the hardware limitations and our future works, we can see that the limitations were that we could only use a data set which only represent the sun or the natural sunlight. We could not use like a snow or rainy or foggy data set because of the scarcity of data and lack of proper hardware. The other limitation was to implement our procedure in a computer given environment, because we could not gather potent hardware to implement our process. And the future works of our project includes extension of dataset, we wish to extend our data set further to foggy and rainy data sets to make our work more adaptable and versatile to different changing scenarios, and we wish to implement different neural network platforms to further enhance our credibility and achieve more faster processing. Finally, to conclude, the paper proposes a new approach to eliminate the difficulty of in object detection for color changing objects. We believe our approach will not only close the gap in development of enhanced object detection platform, but also contribute to computer vision domain.